Yes. One. Okay. In a minute.
Just reach.
Okay. Okay. Perfect. Good. Okay. Good afternoon.
Just give coffee break is too short.
Yeah.
For a limited time.
Okay. Okay, then we start. Okay, thank you. Good afternoon. My name is Sergei Varkentin. I am from the Welding and Joining Institute in RWTH Aachen University. And yeah, today I will talk about modeling gas metal arc welding process and specifically on the requirements of SPH algorithms for that purpose. This. Where is it? Yeah, okay. I will give a short motivation why we are doing that, and also a small introduction into the welding process, what physics are necessary, and what problems do we have in this process. And yeah, after that introduction, I think it's will be clear why we are choosing SPH for modeling the process, and I will also give a small introduction on the solver that we are using. And after that, we will see some results and discuss about them. And at the end, I will show up the still research that is needed to to improve this simulation process. Okay, let's start with the motivation. So since we are a production institute, we deal with melt-based products. And here you see the phase change cycle. And the main problem of the cycle is that when we start with a material of a kind, and after we have the melt formation, so the energy integration into the material, and when we have formed our desired form, after the solidification, we get a product that is of another kind. It is has another structure and another geometry. And the main problem of that is it's the result of the density changes. So we have a volume contraction, and yeah, and at the end we have this gap, shrinkage of material. And this is typical for all production processes that deal with melt base with melted material, which welding is also a part of. And this is also typical for as well plastics as also metals. And in our collaborative research center with the name Precision Melt Engineering, we want to predict, control, and also compensate this effect of shrinkage and the resulting failures out of this shrinkage. And now, short excursus to the welding process. I will introduce only the gas metal arc welding process. There are also numerous other processes, but we will stay with this one. And here is also another process variant of gas metal arc welding. It's called short arc. What is important? We have a filler material in the form of a wire that is fitted automatically. We have two different or two pieces that will be connected, the base material, and with the electric power supply, an arc is ignited. We see the phases where the arc is burning, and we also see phases where we have short circuit. And that is important for later considerations. And here is shown the phase change cycle specific in gas metal arc welding, or the process chain. That is how the material is proceeding. We start with a solid wire and with a solid workpiece. And when the heat is introduced into the material, a droplet is formed. The metal is liquid, and also the workpiece is liquid, and we have droplet formation and detachment, and by that also a melt pool dynamics. And after the solidification, we have here a typical cross section of a weld seam, and with the solidification of the weld seam, a solid joint is then produced. What problems do we have, or what challenges do we have in modeling this, specifically for modeling the metal transfer and the weld seam formation? We already saw this process chain, and we saw that we have a heat input. We have to consider electromagnetism and also the solidification, but it was not the whole truth. It is also very important how the arc is attached to the wire and to the melt pool. We have a strong coupling effect on the surfaces because the surface temperature influences the properties of the arc of the plasma, and by the properties of the plasma, we have another distribution of heat flow into the surface, and also another distribution of electrical current. With the electrical current distribution, we can manipulate the fluid dynamics inside the pool. So the Lorentz force can act in a different way. And by this process, the solidification can also be controlled. So that's the intention of the whole project. And as we see, the effect of the arc is very important and should be captured, but also the interface between solid, liquid, and plasma, because how we see on this picture, the wetting of the arc on the surfaces. So we have to capture and to resolve the surface dynamically, and to know where the phase change is between plasma gas and the solid or liquid. And as you also see here, you do not see it. It seems like it's plain, but the melt pool is always not plain. It is also arbitrary geometry that have to be resolved. And next challenges that we summarized under the technical aspect about the discretization and the calculation time. So we saw it is a free surface deformation that we have there, complex mass transfer, and we have to resolve the high gradients, the field variables. And when we compare the arc coupling, so the electromagnetic task with the heated mass transfer task, we have very different time and space scales. Still, there are techniques that enable the solution of this problem, but yeah, the main problem with that is the simulation duration. Here I have an example of a laser-assisted cladding process that we have calculated, and here we did not include the arc. So the droplets are just a material input. The arc is included as a heat source on the surfaces. And on the lower side, you see an example from France where they considered all the physical effects, and we need more than 120 hours of simulation time. This is this can be done in a academic context for research and to understand the processes, but for industrial application, it is not feasible. So long computation times, and so the approach would be to decompose the domains, and also to separate the electromagnetic task from the heat and mass transfer task. And so that's why we come to smoothed particle hydrodynamics, because in this method we see a big advantage for us. That can resolve the topology changes dynamically, and we do not have to handle all the space where we do not have the mass. That is important for us. That's why we have chosen this method. And we use this open source stage simulator. It's called Splish Splash. It is developed by Professor Bender and his team from the Visual Computing Institute, also situated at the RWTH in Aachen. And it offers fundamental or all necessary models for solid and fluid treatment. And I have some examples of that here. On the lower side, you see an example for thermal spraying. It is used in surfacing technology. And on the upper side, you see another welding process. It's called thick spot welding, where we have introduced an external force field to model the Lorentz force on the fluid dynamics. And yeah, this is an example of this tight collaboration that we need from the basic methods to engineering applications, but also the other way around to show what is needed and to show the developers which aspects are important. Now, specific to our results, or for the models that we calculated the results, we separated the task in three domains. I would say we have the anode, which is normally positive polarity with the wire and the droplet, and the cathode that is normally negative in gas metal arc welding, and we have the arc in the middle. But we cannot, in the actual implementation, we cannot calculate the arc directly because of the high ratio of the density change, and so we will use some models to implement the arc effect on the process. We use particle selection on different aspects like geometric or temperature, or for example in surface like you see here. These are the regions where the arc attachment happens, and in these regions also like I already said, the high density ratio, and we also cannot implement electromagnetism in this example or the actual model status, because we do not have carriers for information between these domains. So here is an empty space, and that's why electromagnetism is not a part of the calculation, but we can consider the arc effect, for example, by the electric current density distribution. So we have a volumetric distribution of the electric current. Here you see in blue the arc attachment, and when this arc attachment is defined, the heat input from the arc is implemented only on the surface that is calculated there. And for consideration of the electromagnetic force, we introduce a volumetric force that is acting on the liquid part. And well, in general, the goal is to capture the phenomenological effects, because to capture all the physics, it is again then not applicable, and a very difficult task. And the main aspect is the temperature variation, because with that we come to a density variation. And one example for that is the Joule heating effect. We introduce it as an additional heat source in the material, where the temperature then is raised. And for the solidification, I want just shortly to introduce to you the Mashi zone. This is a concept because the solidification does not happen at one temperature, but in a temperature range. When the dendrites, so the crystals, begin to grow, they produce kind of an obstacle for the flow field, and so we have to consider a momentum sink in momentum conservation, and this is done based on the Kármán-Kozényi porosity flow. And yeah, the solidification is also modeled then with artificially high viscosity after the solidification temperature. So with this consideration, I come to the results. First example is a different gas metal arc welding processes. Here is a process variant spray arc. It is typical for high energy input, and as you see it right now, we have a burn through inside the workpiece, which is a big failure, and it should not happen at the production site. And another example is a bidirectional wire control. Here, the specific is the wire movement. No, that is hanging. And by this wire movement, the droplet detachment is enhanced. So we have not to bring so much energy, so much electrical energy to detach the droplet. And this process is typical for lower heat inputs. And with these examples, I wanted to show the stability that is a great advantage for us. That we have that great topology changes like the burn through or the droplet detachment and droplet formation, and this is not a problem for this method. What with grid-based method we had big problems in showing that kind of simulations. And another example is for different joints. This is an example of T-joint and the lab joint, which are more than 70% of industrially used configurations of welds. And here I wanted to show that yeah, it was no specific effort on digitization necessary. We just adjusted the plates and used the same models, but we obtained different weld geometries, showing this yeah, big capability of the model to work on different configurations. And in all the cases that you saw, we had 300,000 particles, and this simulation took less than 20 hours of time. Another last example is about modern production process. It's additive manufacturing, and here it is important to bring like a lot of material into the substrate. So we have high number of layers and very big structures, and so we have to even more accelerate the simulation. And our approach was to do a coarser discretization. So we assume that the droplet from the wire is in the range, so the particle is in the range of the droplet. And well, the focus here is to simulate or to predict the component geometry overall and the temperature field inside it, and how the droplet is formed and how it's detached was not that important, but it is considered by compensation models, for example, that it comes with a specific temperature and not that just as cold. And here with this example, we could obtain a result within 5 hours and generate a structure with 20 layers. I will not show you the whole, all of the 20 layers. And yeah, to draw a conclusion, we saw a model for heat and mass transfer, and we saw very comparable results, well, qualitatively very comparable for realistic processes and also for different weld seams. And we also are able to capture surface deformation for very different topologies, and also the stability of the solver that could be an option to detect process limits, because to detect it in an experimental way, it's expensive, and here we can show that with these parameters the process will not work. And the main conclusion is that we treat the physical effects separately, so mass and heat transfer with SPH, and the arc simulation will stay for the Euler's methods. And we saw these two concepts for different discretization levels. And remaining work or remaining research work will be on the variable density, which is still not implemented in this version. And here a small example where we work already on the validation of that to show it the right material behavior. Okay, with that, I'm glad to hear questions.
Yeah. So how did you model the viscosity of the material?
Well, it is a lookup table. So we have the material table, and it is part of the Navier-Stokes equations. They were discretized in the SPH formalism, and so that then it comes. Yeah. Yeah, it was maybe visible here. Okay, it was not visible because the diagram had this high this high values here, but here it has a temperature dependent behavior in the liquid region.
No, okay, so as you do not include electromagnetism of the arc explicitly in any way, does it limit the kinds of wells that you can model or range of currents or voltages?
Yeah, that is the question of the arc attachment. Of course, it will be different, and we have to adapt or to calibrate our heat input parameters by that. But just changing these parameters, I think yeah, we are not at this point where we can do quantitative comparisons, but when we see the process on the video, like in the real experiment, we try to produce something comparable to show the advantage and to the capability of this method. But we are on the way to also bring the like the current and the voltage as a parameters for better capturing the electromagnetism. Yeah, but now at the moment it's just overall heat input that is distributed on the surfaces I showed here. No.
I have one question.
Yeah.
In the machine room, you just use passive flow simulation.
Yes.
So the outside of the machine room, you just use SPH. Then what boundary condition are used in the interface at the machine room and the fluid? Yeah, that's the boundary condition.
So it is the same material.
Yeah.
It is all the same material, but only the viscosity is changing.
But in the machine room, you just use the Darcy. So in the Darcy flow, also using the SPH or something else?
Yes, it's the same. So just fluid flow. So we use the impulse equation, and the impulse equation has a momentum sink that is considered by the Karman-Cassini. Yeah.
The same equation is applied to
the whole video. Genau. Yeah.
Yeah, okay. Okay, thanks.
Thank you. Oops.
Is that? I think so. Yes, I was just talking really low. Okay, just where's the stick? Oh, okay. So, good afternoon, everyone. My name is, can you hear me first of all? Okay. And my name is Paolo Proia, and I'm here to talk to you about my study on heterogeneous heating sources in melting that I did in collaboration with Professor Mauro Sbaraglia and Professor Giacomo Falcucci. So, in the course of this presentation, I will introduce you to the problem and to the motivation on why it's interesting, of course. And then I will show you our chosen methodology and setup for simulations. And then, since we developed our code from zero, I will show also some benchmarks to validate it. Finally, I will show you some results on the proper problem and some new things that we have done. And if there's time, I will show you some new stuff we are working on, but just if there's time. So our study primarily focuses on phase change materials. What are phase change materials? They are materials with high latent heat, and so they can absorb very large quantities of energy during the phase transition. This is very useful in many applications. For example, we have renewable energy, electronics, and thermal insulation, just to name few. And of course, we can recover the energy with the inverse phase change process. So going on, we have that the dynamics of a phase change materials, in this case, a material that goes from solid to liquid, involve both convection of the substance and the melting. This, as we can see in this qualitative picture, gives a very nonlinear dynamic. We have here the substance that is solid and an heating source on the left. And we can see that thanks to the interaction of the melting, the temperature gradient, and the gravity, the melting front, which is the boundary between the liquid and the solid substance, is strictly nonlinear. Moreover, since this is a moving boundary, we have that this influences the transfer too. We can do experiments for this case and this type of problems, but they only yield macroscopic quantities. So if we want to do a local study, we need to do simulations. Okay, so the basic setup that we considered is the one from the figure before. So we have a square cell that is also doable in real life with dimensions of about 0.1 meters. We have the heat source at temperature TH on the left side. The enclosure is filled with a solid at temperature TC. It is subject to gravity, and then we have 3 insulating walls on the other remaining sides. So we have to introduce, of course, some relevant quantities to study this system. The first one is the Nusselt number, which is essentially the ratio of convective heat to conductive heat. And it, of course, depends on the thermal diffusivity of the fluid. And we can measure it here near the heating source as the derivative of the from the derivative of the temperature field. Then we can introduce an adimensional time that will result useful later for some scalings, and it depends on the specific heat and the latent heat of the system, other than the thermal diffusivity and size of the system. Finally, another useful quantity is the average melting front position, which is simply the average over the vertical domain of the melting front as defined as the boundary between molten and solid. And so we simply average it and study it in time. Going on, we have to simulate, of course, the Navier-Stokes equation coupled with an advection diffusion equation that advects the temperature according to the fluid velocity. So we have the continuity equation with density and velocity, the momentum equation where we have viscosity and the pressure gradient, and then we have the interaction with the temperature in the form of the buoyancy term, which depends, of course, on the temperature, on the gravity, on the expansion coefficient of the fluid, and these are our reference temperature and density. In the advection diffusion equation, we have also the melting term, which models the melting, as its name says, and it depends on the specific and latent heat of the fluid, and on phi. Phi is the liquid fraction, which is simply defined as the ratio of molten to solid substance molten substance to total substance inside of a neutral fluid. And it is 1 if the solid is completely molten, and 0 if we are in a completely solid situation. So it's not working. Okay. Of course, other than the equations, we need proper boundary conditions. As anticipated, we have 4 solid walls, so we have to have vanishing velocity in proximity of the walls. And regarding the thermal dynamics, we have one source, which is permanently at temperature TH, and insulating walls. That means that the perpendicular temperature gradient must be vanishing. Of course, we chose to use the lattice-Boltzmann method and I will go fast here because I think everyone knows about this, where we evolve the discrete particle distribution, and we have a collision operator that relaxes it to an equilibrium in a characteristic time tau. And then with a source term, we can model the buoyancy force from the moments of the distribution in the velocity space. We can recover the macroscopic fields such as density and momentum density. This clearly gives the advantage of having very few the kinetic degrees of freedom and to recover the hydrodynamics. We chose to use a D2Q9 lattice with a single relaxation time BGK collision operator. So the new thing is that this can also be used to solve the advection diffusion equation, and we do that by using a second lattice-Boltzmann distribution, which I called G. And it has its own relaxation time tau g. We can see that the lattice-Boltzmann equation is practically the same. The only difference is in tau g, and in the source term that here implements the melting instead of the force. We have that from the tau g we can recover the thermal diffusivity, and that from the 0th moment in velocity space we can recover the temperature field. So again, with very few kinetic degrees of freedom, we have the advection diffusion equation. Of course, I must say that D2Q5, since it is a diffusion problem, would be sufficient. But for practical reason, we chose to implement a D2Q9 even for the G distribution. This was practical, but it also resulted in better scaling results that I will show later. So for the boundary conditions, again, we have a very straightforward implementation thanks to the lattice-Boltzmann. For the solid or insulating wall, we simply use the bounce back condition on the populations and we bounce it to the opposite direction. While for the thermal source, we simply put it at equilibrium corresponding to the source temperature at each time step. Okay, let's move on to the benchmarks really fast. The first benchmark that we did was only temperature and fluid dynamics without the melting, and so we chose the Rayleigh-Benard system. We know that depending on the Rayleigh number, that is the ratio of buoyancy to dissipation, this has a transition between a conductive and convective regime. And we have that for our chosen system, the critical Rayleigh number was about 1,707. To this, it corresponds under this value, we have the conductive regime, which is for with vanishing velocity and linear temperature gradient. While if the Rayleigh number is greater, we have the typical heat plume and the velocity vortices. Okay, we investigated the critical Rayleigh number by plotting the kinetic energy. We know if the velocity is vanishing, so in a conductive regime, we have to have a vanishing kinetic energy, of course. And then if we are in the convection, we have to have a stationary value. We can see here that the change happens in this zone, which is between 1,707.55 and 1,710.60. And this gives an error of 0.6%, which is quite satisfactory, so we did not investigate further. And we moved on to the second benchmark. No, sorry, too much slides. Okay, which was the second problem. This is essentially a one-dimensional problem that only cares about the melting dynamics, and it is described by this equation here. We have known analytical solutions for the temperature field and the average melting front position, which depend on a parameter beta that is defined as such, and it depends on the Stefan number. For our case, we chose a Stefan 1, and we have that the parameter is about 0.62. Here, I plotted some the solutions analytical for the average melting front with black lines, and we did this for different values of diffusivities, and we can see that our data plotted with the dots has a perfect match with the analytical solution. The solution here are normalized, of course, with the length of the system and the number of iterations. Okay, moving on, we can simulate the complete system. So we combine both dynamics of temperature and melting. And here we do not have any analytical results, but we have some results in literature about some scaling laws. Namely, those are for the Nusselt number for small time. So we have that it goes like the inverse square root of the adimensional time. And more moving on in time, there are some convective contributions that emerge, and these are proportional to the adimensional time to the power 3/2 and the Rayleigh number. From this law, we can derive that there is a minimum in the Nusselt number that goes like the Rayleigh number to the power of 1/4. And to this, it corresponds a theta, which goes like the Rayleigh number to the power of -1/2. Then we can define the behavior for large times. In particular, if we define θ2 as the time that it takes to the melting front to reach the right side of the enclosure, we have that this scales like the Rayleigh number to the power of -1/4, and to this it corresponds a Nusselt number that goes like the Rayleigh number to the power of 1/4. We can verify these relations with a compensated plot, and we did this fixing the Stefan number and varying the Rayleigh number, and we have that here our data is plotted in green, and data from literature is plotted in red. First of all, we can see that for our data, the plot is pretty constant, so we know that it respects those laws. And we have also a good match with the data in red, and even slightly better constant behavior. And this we ascribe to the usage of the T2Q9 lattice instead of the T2Q5 as they do in literature. Okay, then we decided to do something new, of course. And we did this by inserting perturbation inside of the heating source. This has already been studied for other thermal dynamics problems, but never for melting. So what we did was inserting a fixed percentage of insulating material inside of the heating source and varying the length of the insulating patches. We can see here that this is an insulating patch. And we also moved the parameters to high Rayleigh number and lower Stefan number to get close to real-life scenarios. And we studied the effect on the transfer and the melting front. Okay, these are some qualitative picture. We can already see that the behavior is quite different from different lambdas, especially evolving in time. In transient times, we have very different behavior that then starts to converge again. For a more quantitative picture, we can, for example, plot the average melting front in the adimensional time, and we can see that varying the lambda, the melting front slows down. We can ask ourselves why, and we thought that this is due to the interaction of the different plumes that we can see here in the slide before. We can see that here there is interference, and so this could influence the melting front and heat transfer. Moreover, if we plot a snapshot in time of the average melting front, we have that it has a minimum. And this is worth studying, but we did not focus on this for now. So how do we compare it to an homogeneous case? Of course, we cannot use the naive assumption of using TH because it's clearly a different mean temperature here near the boundary. In fact, what we did was plotting the average, the spatial average of the temperature near the boundary, and we can see that it has a very dynamic evolution. So we decided to use two equivalent temperatures. The first one was the stationary value that is clearly reached for every different lambda. And the other one is simply the time average of this spatial average over this domain. We can plot the same plots even for this. And we can see that, first of all, these two temperatures are almost equivalent both for the Nusselt number, so the transfer, and melting front. But we can see that these are homogeneous cases, and we can see that they respect the scaling that I announced before. But here, for the inhomogeneous cases, the scaling is different. So probably this is due to the effect insertion of the patches, and this is a point that is worth studying. And these findings we submitted together with my supervisor to a journal, and we are waiting reviews right now. And so to recap, the goal of this was my master thesis, and the goal was to develop this lattice Boltzmann code that could simulate the convection melting. We obtained a good match with analytical solutions. We obtained a good match with literature, and we also found some new interesting results thanks to the insertion of the heterogeneities. Now, for the future, we decided that, of course, an analytic characterization more thorough of the insertion of these heterogeneities is due, and it's also very interesting, as I've shown you in the scaling differences. And also we can insert other, since the code works quite simply, other types of complex boundary conditions, for example, roughness. We can get closer to real-life parameters. And this is because with the low 7 numbers, the simulation gets slower, so we need more time. And so also code optimization is paramount. I think I am out of time. Yeah, I'm out. 5 minutes, wow, really? Okay, so what I could do is that for now, since I graduated, I managed to do some optimization in my code, so we could get closer to real-life parameters. And also, in the meantime, we managed to start a parallel study. We used the insulating patches in the first study. Now we are using fins. So what do fins do? We know that they speed up the melting inside of the enclosure, and we can find studies, of course, in literature, and they use mostly conductive fins. We did something different a little bit, not much. So we use the sources. So they are immediately at TH. And for now, we started with a single one, and we have intention of implementing multiple, of course. So what we did was a parametric study on how this enhances the melting. So what we did was run various simulations, varying the fin position and length, maintaining a fixed surface, and see how this influences the total melting time. So in this plot, you can see that on the x-axis, we have the length, on the y-axis, we have the height, and the color map is the total melting time. So when the enclosure is fully molten, and this is normalized to the melting time without any fin. We can see that this is non-trivial, as we favor very low and very long fins for a faster melting time. And I show very fastly some more qualitative results. This is the Nusselt number, but of course, this is a very, very early stage study, so it's kind of ugly, sorry. And we can see that we have, again, complex behavior. And of course, the melting front is no longer a good metric because we have that the fin offsets it by much, by its own length. Okay, so it's already closer to the left side. So we studied the normalized liquid fraction, and we can see here again that lower fins with that are longer are faster in melting the substance. Okay, so again, the goals are kind of the same for this study. We have to do this parametric study more thoroughly. Currently, we are varying the Rayleigh number, the Stefan number, and seeing if this influences the plot from before. And so we have to explore a wider range of parameters, characterized analytically this fin constitution, and again, code optimization, and maybe some experiments that we are starting to get materials for. Okay, so now I'm done. Sorry if I went for too long, and thank you for your attention.
Okay. No, I just have one question. How is the volume fraction of the liquid phi, the parameter phi in your energy equation?
Okay, we use the enthalpy. We use the enthalpy, so I did not insert it in the main slides to not bore people, but we know that, of course, the liquid fraction is a function of temperature, but we have that in phase transition, temperature is not very good because we know that phase transitions correspond to jumps in the system, in discontinuities. So what we did was using the enthalpy, which is a good function. It's better than the temperature because we can smooth it, and then we can directly, from this formula, we can translate this to a smoothing of the liquid fraction, introducing two fictional enthalpies for the liquid phase and the solid phase that, of course, simulate this jump. And we did it like that.
So you just use this parameter to modify the movement of the interface?
Yes, we use the enthalpy. We give from the temperature, we get the enthalpy, and from that the liquid fraction. That over a certain threshold means that the hydrodynamics are initialized.
Okay, thank you.
Thank you very much. Thank you very much.
Yeah.
Hello, everyone. I'm Ruixin Li, and I'm glad to share my work with you. The title of my presentation is Coupled Phase Field Lattice Boltzmann Method and Discrete Element Method Model for Three-Phase Interaction Problems. My content is divided into 4 parts. First, background. The reason why I want to develop a model for the three-phase interaction problems, and methodology. How am I developing this method, and how to validate my model, and what my model can do. First, the background. As we know, the gas-liquid solid interaction problems is complex and have a great importance at lots of processors. Therefore, we need a proper method to study this problem. Lee and McMinn studied the poromechanics through the experiments, and we found that it's a little bit hard to get the full field data compared with simulations. And in the specs of simulations, Jiang integrated color gradient lattice Boltzmann method and discrete element method, and captures the complex phenomena in the gas bubble coalescence and breakup, and but the density ratio in their model is set to be unified, and the perfect wetting conditions are set on the solid surface. And this is phase model. This model, he used this model, he integrated the pseudo-potential lattice Boltzmann method and discrete element method, and use this method to simulate the drop impact on deformable porous medium. While in this model, the density ratio is around 20, which is lower than the realistic water-air density ratio. Therefore, in order to simulate more realistic simulations, we need a model with larger density ratio and adjustable wettability. Speaking of large density ratio, phase field lattice Boltzmann method is a powerful method. Here we apply the phase field lattice Boltzmann method proposed by Liang, and in this scheme, the Allen-Klein equation is used to track the evolution of interface between gas and the liquid, and the phi in the equation is the order parameter used to identify the liquid and gas. And the Navier-Stokes, incompressible Navier-Stokes equations are used to simulate the velocity field and the pressure field. And this Fs and this Fs is surface tension force, and gravity and G is gravity. These two forces are considered in our model. For the movements of solid particles, we apply the Newton's law, which means that the change of velocity is caused by force, and the change of angular velocity is caused by torque. And in order to solve these equations, we choose the lattice Boltzmann solvers because this solver is simply when we simulate the case, including the porous medium. And we can find that there are two equations. The equation for the equations of f is calculated for the Allen-Klein equations, and the function g is calculated for the incompressible Navier-Stokes equations. And for the solid particles, we applied this Verlet's iteration method. The equations are shown here. And in our model, we should not only we should calculate the fluid and solid motion separately, but also we need to calculate the interaction between the fluid and solid. One of the most important interaction from fluid to solid is the hydrodynamic force, which can be calculated by a scheme imposed proposed by Wen. And another important interaction from fluid to solid is this capillary force. This capillary force is calculated by these marked nodes. First, we need to find the nodes which belongs to the fluid, and the density is between the gas density and liquid density, and near to solid particles. With this distribution of marked nodes and the local density gradient, we can calculate this dirt phi, and then we can get the capillary force on each particles. And in our simulation, there will be lots of curved boundary. Therefore, we need a wettability scheme to calculate the wettability on the curved boundaries. Here we provide the improved virtual density scheme, first imposed by Li and then modified by this paper. This scheme is first applied to pseudo-potential lattice Boltzmann method, and according to our test, it's worked well in the phase field lattice Boltzmann method. And for the streaming step, we can find that when the curved boundary is considered, the distance ratio between fluid nodes and solid nodes can't keep to 0.5. Therefore, when we calculate the streaming step at the curved boundaries for the Navier-Stokes equations, we need interpolation bounce back scheme. By integrating these two schemes, we can find that we can achieve different wettability through different dirt phi. Last but not least, the force acts on the particles, including the collisions between particles. And in this model, we use the soft contact model, which means we need to calculate this force using the overlap area. That will cause a problem when we calculate the interpolation streaming scheme. The minimum gap should be larger than 2, which means they are contradiction. In order to solve this contradiction, we define a shrinkage degree, which means when we calculate the flow field, the radius of particles will be smaller. And so we, by integrating all the schemes, we can have gas, liquid, solid model. Now we want to validate our model. First, we choose this think of one calendar benchmark case. Compared our simulation results with the experimental results, we found its match well. Another benchmark case is self-assembly of 3 cylinders. The three hydrophilic cylinders floating at the interface of gas and liquid, and they will be attracted by each other and finally get in touch with each other. We also compared our simulation results with John's paper, and we found that the movement tendency is matches well. And now we successfully get a correct model, and we want to use this model to simulate the gas penetration into constrained deformable porous medium. The setup is shown here. Some particles are placed in the computational domain, and the left and the right boundary are rigid walls. The gas flows into the computational domain through the inlet on the bottom at a constant velocity, and the fluid can flow out through the outflow boundary on the top. There is a permeable mesh, which means the fluid can flow through this mesh freely, but the particles will be blocked. And the particle radius is set to be evenly. And from our simulation result, we can divide this process into 2 stages. Stage 1, we found that the gas will propel solid particles and form a gas bubble. All the solid particles are distributed between bubble, permeable mesh, and rigid wall. In stage 2, gas continues to flow upward, penetrate into the porous media, and the particles immersed in the single phase will fall down. And through our simulation result, we can find that the main propelling force is capillary force. Therefore, we try to adjust the surface tension coefficient and study the effect. We set the surface tension coefficient from 10 to 50. And we can find that when the surface tension coefficient is small, the gas tend to form a sharper bubble. And for the large surface tension, the gas tends to form a round bubble. And we can find that when the surface tension increases from 10 to 20, the gas penetration rate increase. That's because when the surface tension is small, a sharp bubble formed, but the propelling force is small, so the penetration rate can be bigger a little. And if we continue to increase the surface tension coefficient to 30, and we found that the tendency to form a sharp bubble keeps, and the propelling force become bigger, and the penetration rate reaches the biggest rate. But when we continue to increase the surface tension, the gas forms a round bubble, and we can see the front area increase, and this will hinder the gas penetration into the porous medium. And this is our conclusion. We successfully developed a gas-liquid-solid interaction model by integrating the phase field lattice Boltzmann method and discrete element method, and improved virtual density scheme is implemented in phase field lattice Boltzmann method. And the two stages are observed in the gas penetration into the constrained deformable porous medium. And with the increase of surface tension, the gas penetration rate increase first and then decrease. This is our problem solved. First, we need to develop a method for calculating the particle distribution function at the narrow gap, so we can erase that shrinkage degree. And also, we still need to find or develop a phase field lattice Boltzmann method for large density liquid gas density ratio simulations. And I'd like to gratefully acknowledge the suggestion from Professor Liang Hong and Dr. Zhang Xitong. That's all. Thank you. Yes.
How you communicate with each other? I just wondered which calculation sequences because they just perfectly.
In our iterations, we first calculate the motion of we first calculate the motion of fluid field, and then the particle distribution functions change, so we can get the hydrodynamic force and the capillary force. Using this force, we can get a force acting on the particles, and then we use this force to let the particles move, and the next iterations.
So when you're updating your solid location, your solid boundary also comparing the external force with the hardness of your solid material.
At the deformable porous medium means the distance between particles will change, but this is rigid wall, and this also rigid wall. They don't deform, just the particles.
What technique are you using to reinitialize the cells that were under the particles in terms of determining what phase is existing?
Yes, you mean if the particles moves and we need to reinitialize this? Yes, here we use the scheme. The scheme we used is the non-equilibrium scheme, which means we can get average the density. Let me take density as an example. We can get the average density through the fluid nearby, and the velocity can calculate it by the particle's velocity, and we can get the equilibrium particle distribution function, and we can average the neighbor's non-equilibrium part and add on this equilibrium particle distribution functions. Am I clear?
Okay, thank you. Okay. Thanks all.